Shooting it raw?
Yes. Shooting it raw. We are looking at an image that... Okay, let me describe it. So, in terms...
That's going to be interesting.
Okay, yeah, so it's not a photo... Well, it's a graphic. It's not... Is it strict? It's not a photograph. It's a rendering.
No, I mean, it's a photograph.
It's a photo?
Yeah.
At 10 micrometers?
No, that's the scale. So this bit, which is like, I don't know, a thumbstick, is basically the length of 10 micrometers.
Okay, how long is 10 micrometers?
It's 1/100th.
Assume I'm an idiot. 1/100th?
1/100th of a millimeter.
1/100th of a millimeter. So, okay, like you can still kind of picture it. Okay, so the image is... It's in square format. It is, it's, imagine looking at a very kind of 3D spider web where the spider is deep lost in a cone, but the webbing is yellow with some green and there's purple, and I assume these are all colorized. It's a colorized graphic. It's not actually light that we're looking at.
Yeah, I mean, it's something which the software describes with a certain signal.
Okay.
So but the signal had a specific wavelength. And
right.
But
okay.
if you would look directly, I mean, like, this is a microscopy picture, obviously,
yeah,
right?
Yeah.
So you could actually see the colors by eye. So they're in the visible light range.
So what would it just look, since it's tissue, I mean, okay, because of what you are professionally, I assume this is some kind of tissue. It looks like fibrous. Okay, so in between the yellow and the green and the purple, there's like kind of black. I guess the purple is space as well, but the black is the kind of negative space, I guess. And then, so there's this like, it's like looking at a sponge, I guess. And, so why would you call this a portrait of your mother? No, clearly not. No, I'm an idiot. No. Of course not. It's not a portrait of it. It's okay. So what is this? What is it? What am I looking at?
These are actually two cells, which are stained. So the blue is actually the cell nucleus. Okay. So the DNA is stained in blue.
Okay.
And that's actually what is the cell, and what you see else is actually outside the cell. So, so the black spaces are actually not empty; they're just not stained, but everything is like super full. And this picture was stained for fibronectin and hyaluronic acid, and these are two extracellular matrix components. So what you find as a scaffold around the cells.
Okay.
So this basically shows that if you have cells in a tissue, in a petri dish, they are making their own scaffold.
Okay.
So, and this was a very, I like the picture for two reasons. The first one, it is extremely pretty.
Yeah, it is.
And you can basically see like how nature creates things which are just beautiful. It is a piece of art in a way.
Yeah.
And on the other hand, this image was a piece of cake, and actually it's the wrong staining.
Okay.
So,
wait, when you say it's a piece of cake?
Well, in a way, so when we tried to publish this picture as a part of a manuscript, we got a reviewer who didn't believe that our red staining, which is the hyaluronic acid, is going to be actually hyaluronic acid. So he was doubting that. And he was right in doing that. Because, so what this is we have fluorescently labeled antibodies which bind to specific antigens. So one of them is fibronectin, the other one is supposedly hyaluronic acid. And we get those commercially. And it turned out that the antibody for hyaluronic acid was actually staining something else and not hyaluronic acid. And we built like a whole storyline over this, because it was about like what kind of role hyaluronic acid plays in fibronectin fibrogenesis, so which is basically the making of fibronectin fibers, which you need to make a scaffold, like this network. And in the end, we were staining something which was not hyaluronic acid. So there was like a lot of work and time and research money going into it for something which actually was not 100% true.
Right. Okay. Okay, so looking at it now, I can see that there is some reddish stain, which I maybe didn't mention, closer to the blue Now, the blue is the cell, or the blue is the nucleus?
The blue is just the nucleus.
Wow, okay. But so you can see the red, and you can sort of see yellow and the bleeding into the green and all this stuff. Now, assuming I don't understand what you're talking about, which I don't, what's interesting here is that you're making the scaffolding, which is basically the structure that is forming around the cells, or the cells are making it. Like, why is what's happening here of interest?
So normally, there are two things about the extracellular matrix, and I'm really fascinated with the extracellular matrix. So one thing is, when people think about tissue, they just think about the cells. But especially if you go in tissues like, for example, the bone, there are actually not that many cells inside. It's mainly just matrix. So matrix actually makes up a major part of the total body. Actually, collagen 1 specifically is the major protein component of the human body, and it's not inside the cell, it's outside of the cell.
Okay.
And you can think of it like if you have a human and a jellyfish in water, they're happy. Once you take them out of the water, you put them on the beach, the human would walk away. The jellyfish will not. It's going to be like all flat and floppy because it doesn't have the skeleton to support it. So the extracellular matrix is like the skeleton of the tissue.
Okay.
So in a way.
Got it.
But it's not only this, it's basically, it has all the signals. So it's kind of like, the cells make it, and it's kind of like an encrypted message. So if another cells come in, it can actually read. And it's not only the biochemical components, so the factors, but it's also the way how they're arranged. So the topography, and also if the extracellular matrix is stiff or soft, so even the mechanical properties will affect how the cells read. So you can use the extracellular matrix to guide biological processes, such as, for example, healing or regeneration. So we are making biomaterials out of this extracellular matrix, and we are trying to kind of encode specific information in it, which will then promote, for example, or regeneration.
For example, blood
growth, blood vessel growth. Like revascularization, basically. That's a big topic.
So, is this part? If this is part of your research, you're just trying to understand the mechanics in order to lead to application, or you're actually trying to develop an application?
I mean, like, we have several projects, and this was to understand what role hyaluronic acid would play in the assembly of the extracellular matrix. Hyaluronic acid is also extreme bioactive. It was actually shown that if you go into like some type of fish, like the zebrafish, or into lizards, which can regenerate, for example, the heart completely, which humans cannot, is that hyaluronic acid is one of the major components which plays a role there. So if you remove it, instead of regenerating, for example, the zebrafish will have a scar in their heart. So things like that. So there are a lot to it, and we wanted to know in how far hyaluronic acid will affect the extracellular matrix assembly. So this picture, in the end, was not part of the final publication anymore, but our hypothesis was not wrong. So hyaluronic acid is indeed needed for fibronectin to form fibers, and it's like, the fibronectin goes first and then all the other components follow. So if the fibronectin fibrogenesis is disrupted, nothing else can be built on top. So that was one of the things.
Wow. Okay. Just trying to wrap my head around it. Okay, so within your team, like, how large of a team is it?
Oh, that depends if we're in the summer or not, because I do have some summer students as well.
So it's through university.
Yeah. So right now I think I have 8, 9.
Okay.
It always comes and
shifts.
goes.
Yeah, for sure. Considering that you're like a total nerd weirdo, right?
Thanks.
You're welcome.
Thanks so much.
No, you're welcome. It's the biggest compliment, because you're using your head to do really fascinating work. Like, how do you listen to, like, somebody who's listening to you, who is in their journey? So, for example, in high school, where this is like years ahead in terms of sophistication, understanding, and being able to separate ideas. Like, how do you connect your life or some kid who's developing and making decisions as they go. Like, why did you end up in this field of all other fields? Like, it's pretty esoteric. It's pretty
esoteric.
Well,
okay.
it's not random. It's really specific, but it's also it's unusual. You're a weirdo.
Thanks so much.
You're welcome. It's a compliment.
In a way, this was always something I wanted to do. I always wanted to go into biomedical research.
Oh, wow. Okay.
And I thought I have to do medicine for that. But
right.
I did an internship in a hospital for like 2 weeks where I followed like doctors through like different different stages. You know, I was in the ICU, diabetes and so.
How old were you at the time?
I think it's 16 or 17.
Okay.
And I saw things which I didn't want to see.
Yeah.
And I also realized that the doctors, they really don't have such a big understanding on like the molecular background.
Sure.
So I think it depends because there are some really good doctors as well, right? So I do actually have some collaborators who are doctors. I'm not saying they don't know what they're doing, but for them it's more like, okay, so this is the symptom, which means this disease and this treatment. But it doesn't mean that, you know, they are so much interested in the background of the disease in a way. And there's also a lot of, I would say, involuntary contact with a lot of strangers.
Okay.
So
Okay, this is it. That's a strange sentence to hear. Okay.
But I mean, like, especially like if you work with patients, you know, like you have close contact, you touch them, you know, like. I felt that the doctors are really getting cold towards the patients, which maybe, especially if you're in the ICU, you have to do. Otherwise, you know, you just get depressed at some point of time. But
sure.
In a way, they sometimes weren't really treating them like as humans anymore.
Right.
And I really didn't like that. Okay. And then with the combination that I was in the room, people were exposed, I was just standing there. I was feeling awkward. I was I shouldn't be standing here. This is private, you know. Plus that it actually did not really cover my field of research interest. So after I got out of the hospital, I was like, okay, it's not medicine.
That's not you.
It's definitely not me. And but I really wanted to do biomedical research.
Wow.
And then I got into an internship doing like cancer research. And there was a really nice professor who basically sat down with me and explained for hours.
Okay.
Like, you know, what kind of genetic mutations there are, what they're working on. That was
just
fascinating.
The exactly.
And then of course I also did some laboratory work, and I like that too. So I do like working my hands. And but that kind of got me hooked. So I didn't go into cancer. Obviously, but. Yeah, I don't know. At some point, I realized during my undergrads that my heart is beating for stem cells. So I went into stem cell research.
Nice.
Yeah.
Foreshadowing, maybe? Or is that where we work in? Stem cells for heart?
Yeah, well, I'm not doing so much heart anymore.
Okay.
But there are adult stem cells, which are called mesenchymal stem cells, which have a lot of really good properties. So, for example, they modulate your immune system. And you think like if people think about the immune system, they always think about, well, it's to deflect diseases or parasite bacteria. But the immune system is basically like a police force regulating everything, like traffic police.
It's always on.
Right? So they regulate a lot of tissue processes and do a lot of the communication. So in a way, by regulating your especially the inflammatory response, you can decide if something is going to heal or not.
Right. You
know, you need inflammation. Without inflammation, there's no healing. However, if the inflammation is wrong or too long, there's no healing either. Exactly. So it's really about this fine tuning, and those stem cells were actually shown to really be able to fine tune the immune system and thereby modulate healing responses and even promote regenerative responses. So people then worked a lot putting these cells into all different places. And but the thing is, you know, normally you put the cells into a diseased area, right? Which can be ischemic, necrotic. So if something is killing the tissue, if you put in cells inside, they are not going to fare better. So they are going to die. So the idea was, instead of using the cells directly, to use what they are making, which actually has this effect. So people have been working on their secretome, which is basically like all the soluble factors, on exosomes, which are like little microvesicles, which contain like a lot of also signaling factors. And I decided to go for the extracellular matrix.
Got it. I understood what you said.
That's good.
Yeah. Shall we go to the next photo?
Yeah.
So is life really a gift? Really? Can you make every second count? That's the whole point of the podcast. So if you like what you've seen and you're inspired, because that really is my mission, then please give it a like, subscribe, and share.
Shooting it raw?
Yes, shooting it raw.